So let's go over this practice problem on hydrograph separation. We've got some data here for a creek called Dinwiddie Creek in Wyoming, and we have about 7 days worth of data. It's a lot of data, which is why we're doing this in a spreadsheet. And our job, if we look at the instructions here, is to separate the base flow from the event flow based on 4 different methods. From a very simple method of a horizontal line up to more complicated methods described in Dingman. So the first thing we're going to want to do is to actually plot the data. So here I've plotted column A, which is the time in days, versus column B, which is the discharge in cubic feet per second. And this is what my hydrograph looks like. It's a typical event hydrograph with the sudden rise and then a fall of discharge with time. Now the first few things we want to do here are identify 2 important points. One is the onset of the event hydrograph, which will be located at the point where the curve starts to go up. So it's going to be somewhere right in here, right where I'm putting this little red dot. We'll look in more detail on the actual data itself, but that's one thing we want to mark. The second thing we want to mark is the midpoint of the hydrograph peak. And that's a lot harder to see on here because you can see that the data are quite messy near the top, but I think you can see that at about 3.7, we actually reach the very peak of the hydrograph. And I'm going to draw a vertical line through there to mark the center of the peak, or rather the peak discharge, the time of the peak discharge, let me say. Then you guys should do this with a straight edge and a ruler, but I'm just going to use the drawing tools in Excel to do it here. So there you go. We have the beginning of the event hydrograph marked with the red dot, and we have the high point, the peak, shown with the blue line, which occurs at about 3.75 hours after the beginning of the record. So we are instructed to estimate, to try to separate this hydrograph into the base flow and event flow components using 4 different methods. And the first method we're going to use is really the simplest, and that's just the horizontal method. So in this method, we assume that the base flow is constant during the duration of the storm and equal to the level we see at the very beginning of the event flow. In other words, we're just going to draw a horizontal line from that red dot all the way across the hydrograph. There's what it looks like. And so we'll describe this as the black line represents the simple horizontal line method of hydrograph separation. Now, the second method we're told to use is the one that's described is the very first of the 3 methods that is described in your reading from Dingman. And it's actually probably the most common method used, minus sort of more complicated chemical and statistical methods. So if we're using simple graphical techniques, this is the method that is most commonly used. And this is the way it works. So the idea of this method is to use that starting point. And what we're going to do is we're going to do 2 things. We are first going to draw a line that's a continuation of the pre-event flow trend. So this trend here, we're going to continue that trend through the beginning of the event hydrograph all the way to the center line there. So we're going to find this point here. And then from this point here, we are going to go a certain number of days forward, given by a formula that relates the end of the event hydrograph to the size of the watershed. And that equation is that these extra days here, D, these days here equal 0.82 times the area of the watershed in square kilometers to the 0.2 power. And that tells us at the time of the end of the event hydrograph, and then wherever that is, say it's over here somewhere, we're then going to draw another straight line between those 2 points there. And that will define the base flow and the event flow above it. So the first thing we're going to need to do is to compute the area of the watershed in square kilometers. It's given here as 88.2 square miles, so we're just going to use Excel's very cool convert function to say convert the value in L1 from square miles into square kilometers. How cool is Excel? So there we go. Our area is now 228 square kilometers, and the value of D here will equal 0.82 times that area in L2 to the 0.2 power. So it's about 2.43. So we're just going to estimate it here now. So if it looks like the beginning of our hydrograph was at a time stamp of about a little less than 2. If we add a little bit more than 2.4, that brings us to about 4.4. 4 point, is that right? I'm sorry, from the midpoint, sorry. So here we're at 3.75. Let's just do that here. So the midpoint was at 3.75, right? Hours from the beginning of our record here. And so the end of our event hydrograph should occur at the sum of those things, which is O1 plus O2. So at about 6.2 days from the beginning of the record here. So 6.2, let's actually do this more accurately here. So 6.2 is going to be right about here. So there we go. So now again, what we're going to do, what you would do is take a straight edge and continue this trend at the end of the event, before the event hydrograph, at the end of the discharge leading into the event hydrograph. I'm going to actually take a straight line and do that here in my drawing program. So I'm just going to take this line here, and this is going to be the extension of the decay leading into the event hydrograph. We're going to color that red. And then we're also going to take another line, and we're going to connect that point to the end of the event hydrograph as predicted by my equation. So I'm going to connect this line here and that line there. And that funny shaped line, that broken line, represents the separation between the base flow below and the event flow above, using, that's the red line, and that's using, this was Dingman's technique A. All right, so we've done the simple one, we've done Dingman A. We also have 2 more to do. So we need to do Dingman's B and Dingman C. Now, Dingman B is really one of the more complicated ones, and let me show you what that is and what the philosophy of that is. So let's use a different color. Let's use green for this here and describe what we're actually going to do. So for this method, the idea is to recognize that the end of an event hydrograph is marked by a transition back to the normal recession curve, where the discharge decreases exponentially. So the idea is we want to find that recession after the end of the event flow and extend it back under the event flow. So if we can sort of say, okay, this looks like here, this part in here, this is the post-event flow recession. We're going to take that and sort of extrapolate that exponential decay curve back into the event hydrograph until it intersects the midpoint here, or the peak. And then we're going to once again draw 2 lines. We're going to use this line, which is the curved exponential decay, and then we're going to draw a straight line here. Straight line here, and that's going to be our hydrograph separation. So the key to this method is sort of back extrapolating that recession we see after the event flow back into the event flow. Now, the idea, we're extrapolating an exponential decay curve, which is a curve, but if we take the log of the y-axis, the log of the discharge, then that exponential decay curve plots as a line. So to do this technique, what we usually do is take this graph and we transform it by plotting it plotting the time not against the discharge, but the log of discharge. And I'm going to do that here by just simply copying this graph, and I'm going to copy it to another place so I don't lose all that hard work I already did. And here's the same exact graph I had before, and now I'm going to change this y-axis. I'm going to make it logarithmic. I'm also going to lower it. It's going to start at 100. There we go. So there we go. So this is now the same graph. We have the same midpoint. Let's actually draw that midpoint in. There it is. And now what I want to do is fit a straight line to the recession part of the curve after the event curve, sort of around 5 to 7 seconds or something like that. And I'm not going to ask you to actually fit a straight line. I'm just going to ask you to eyeball it, which is what I'm going to do here. So I'm going to take a line. I'm going to do the best job I can to sort of fit something that resembles a straight line through those data like this. That's pretty good, right? So That's what I want. So now, in other words, this part of it represents the recession that happens after the event flow. Now, what I want to recognize on this is I want to look at the intersection of that extrapolated straight line to the peak line, and notice that's occurring right about at 1,000. You see that right there is about 1,000. Right there is about 1,000 cubic feet per second. Okay, back to our normal graph. This is not log anymore, but normal. Remember that point on the midpoint was about 1,000. So it's right about here. So I'm going to locate that point, and then I'm going to draw two lines. The first is going to be a straight line from the beginning of my hydrograph, my event hydrograph, to the midpoint, the green point there. And the second is going to be my best estimate of that exponential decay curve that starts at the green dot and goes back down to the recession after the event flow. So this is going to be, let's see, this is going to be a little harder to draw, but I'm going to do the best I can. So it's sort of like a curved line that's going to go like this. There we go. It's not exactly a curved line. It's not perfect. It doesn't need to be. That's good enough. So there is my third method here. This is green now. And this is, we're going to use Dingman's method B. And we get that funny shape there. Again, this is obviously, if we look at this, this is going to predict much less event flow than we did with the red method or the black method, right? So we're going to get different values here depending on what method we use. So the last thing we're supposed to do is use, we'll do this in orange here. We're going to use Dingman's method C, which is sort of like the straight line method, except now that line has a slope. So the idea is we're going to start from the beginning, and we are going to go across along a straight line, and that line is going to now have some kind of slope like this. And that slope is going to be determined by the size of the watershed. And the formula we use to do that looks like this. That the slope equals 0.46 times the area of the watershed in square kilometers. So it's a simple equation, so let's figure that out here. So we know our area of the watershed in square kilometers, and so the slope will just be equal to 0.46 times that area, which is in L2, and we get, it's about 100. And again, this is going to be very much just rough estimate. We're not trying to be super exact here. So it's about 105 cubic feet per second per day. So let me show you how to simply apply that. Our starting point here was about at 500 cubic feet per second in just about 2 days. So we're going to go up, this slope says to go up 105 cubic feet per second per day. So after 3 days, we're going to go up about 100. 2 days, bring us to 4, we're going to go up 200. 3 days, we're going to go up about 315. So we're 5, that'll bring us to 815, which is somewhere around in here again. So this is, the idea here was that this rise here, that's the rise, and this is the run. So this was 3 days, 1, 2, 3 days. And so the rise would be 3 times this 105, or about 315 cubic feet per second. And that brings us to about the orange dot. And so drawing a straight line there, then at that slope, would produce, there we go. So that is our, let me get rid of the other ones, but that would be our fourth hydrograph separation technique. And if we had to rate them in terms of the amount of event flow that they predict relative to base flow, we'd say that the red technique, Dingman A, produces the most event flow. The straight line method, black, produces the second most. Third most would be the orange, Dingman C, and then Dingman B would produce the least amount of event flow relative to base flow.